Today I am going to discuss about the second colligative property, which is known as elevation of boiling point. So before starting this topic, let us define boiling point of a liquid. So boiling point of a liquid is the temperature at which vapor pressure of a liquid is equal to the atmospheric pressure 1 atmosphere. So किसी भी लिक्विड बॉयल होने के लिए स्टार्ट होता है जब लिक्विड का वेपर प्रेशर 1 एटमॉस्फेयर का साथ इक्वल होता है. एक लिक्विड बॉयल होने के लिए स्टार्ट नहीं होगा, तब तक स्टार्ट नहीं होगा जब तक लिक्विड का वेपर प्रेशर 1 एटमॉस्फेयर का साथ इक्वल नहीं होगा. सो बॉइलिंग पॉइंट ऑफ ए लिक्विड इज द टेम्परेचर at which vapor pressure of a liquid is equal to how many atmosphere? 1 atmosphere. To explain about the elevation of boiling point, let us plot a graph. In this graph, vapor pressure is plotting against the temperature. Suppose this is the graph for the pure solvent. This is for the pure solvent. When temperature increases, vapor pressure of the pure solvent increases, and this is the graph for a solution. In a solution there are two components, one is solute, another one is solvent. So in case of solution also, when temperature increases, vapor pressure increases. Now up to this point, from this point to this point, let us consider vapor pressure equal to 1 atmosphere. So this point join here, from this point this. So now this temperature is considered as TB naught, and this temperature is considered as TB. So TB naught, it is a temperature at which vapor pressure of the pure solvent is equal to 1 atmosphere. Therefore TB naught, it is the boiling point of the pure solvent, because at this temperature vapor pressure of the pure solvent equal to how many atmosphere? 1 atmosphere. Similarly, TB is the boiling point of the solution, because at the temperature TB vapor pressure of the solution equal to how many atmosphere? 1 atmosphere. So TB is the boiling point of solution and TB naught is the boiling point of pure solvent. So according to this graph, so boiling point of the solution TB is greater than the boiling point of the pure solvent. So why boiling point of the solution is greater than the boiling point of the pure solvent? Because at a constant temperature, vapor pressure of a solution is lower than the vapor pressure of the pure solvent. That means when a non-volatile solute is added to a pure solvent, then vapor pressure of the solution will be decreased, but boiling point of the solution is increased. Let us consider in this case boiling point. In this graph, boiling point increases by TB. TB is the increase in boiling point. When non-volatile solute is added to a pure solvent to prepare a solution, let us consider here boiling point increases by how many? TB. So this TB boiling point is increases by how many? Delta TB. So this delta TB is known as elevation of boiling point. So how can you calculate delta TB? Delta TB, it is known as elevation of boiling point. So how can you calculate delta TB? So delta TB equal to TB minus TB naught. So this is the relation to find out elevation in boiling point or increase in boiling point of a solution. So delta TB, elevation in boiling point, increase in boiling point of a solution, is equal to difference between the boiling point of the solution and boiling point of the pure solvent. So it has been experimentally observed that delta TB, that means elevation in boiling point of a solution, is directly proportional to molar concentration of the solution. Small m represents here concentration of the solution in molality. To remove the proportionality sign, let us put a proportionality constant Kb. Here Kb is known as molal elevation constant, molal elevation constant, or it is also known as ebullioscopic constant, ebullioscopic constant, or its unit is Kelvin kilogram per mole. Now delta TB equal to Kb. So molality equal to weight of solute into 1000 divided by molecular mass of solute in the solution into weight of solvent. So this is the final relation. This is 2. So this is the final relation to find out delta TB, or elevation of boiling point of a solution. With the help of this solution, we can also find out molecular mass of solute in the solution. In this relation, so what is Kb? Kb is the molar elevation constant, also known as ebullioscopic constant. So value of Kb is different for different solvent. In numericals, Kb value will be supplied by the examiner. W2 is the weight of solute in the solution, M2 molecular mass of solute in the solution, and W1 weight of solvent in the solution. So with the help of this relation, we can find out molecular mass of solute in the solution. So third colligative properties is depression of freezing point. Depression means decrease here. So it is related to freezing point of solution. So before starting this topic, let us discuss about the freezing point. So freezing point of a substance is the temperature at which vapor pressure of the substance in solid phase is equal to the vapor pressure of the substance in liquid phase. So particular एक substance के लिए freezing point ऐसा एक टेम्परेचर है जिस टेम्परेचर में सॉलिड फेज का वेपर प्रेशर लिक्विड फेज का वेपर प्रेशर इक्वल होगा. सो किसी भी एक सब्सटेंस फ्रीजेट होने के लिए, सॉलिड फॉर्म में ट्रांसफॉर्म होने के लिए, जब फॉर दैट सब्सटेंस सॉलिड फेज का वेपर प्रेशर लिक्विड फेज का वेपर प्रेशर इक्वल होगा, ओनली दैट टेम्परेचर ए सब्सटेंस converted into solid state. So freezing point of a substance is the temperature at which vapor pressure of the substance in solid phase is equal to the vapor pressure of the substance in liquid phase. So freezing point of a solution is the temperature at which vapor pressure of the solution is equal to the vapor pressure of the pure solid solvent. सो पर्टिकुलर एक सॉल्यूशन के लिए फ्रीजिंग पॉइंट ऐसा एक टेम्परेचर है जिस टेम्परेचर में सॉल्यूशन का वेपर प्रेशर प्योर सॉलिड सॉल्वेंट का वेपर प्रेशर का साथ इक्वल होगा. जिस टेम्परेचर में प्योर सॉलिड सॉल्वेंट का वेपर प्रेशर सॉल्यूशन का वेपर प्रेशर का साथ इक्वल होगा, ओनली दैट टेम्परेचर solution is converted into solid state. So freezing point of a solution is the temperature at which vapor pressure of solution is equal to the vapor pressure of the pure solid solvent. So to explain about the depression of freezing point, let us plot a graph in which vapor pressure is plotting against the temperature. So this is the line for the solid solvent, and this is the line for the liquid solvent. When temperature increases, vapor pressure of the liquid solvent increases, and this is the line for the solution. In a solution there are two components, one is solute, another one is solvent. solute, here non-volatile solute. Matlab this is a non-volatile solute solution. So here Tf, it is a temperature. Tf is a temperature. Tf, it is a temperature. At this temperature, vapor pressure of the liquid solvent is equal to the vapor pressure of the solid solvent. So Tf is the freezing point of the solvent. Tf is the freezing, this is the Tf naught. So this is Tf, this is Tf. So Tf naught is the freezing point of the pure solvent, because at this temperature vapor pressure of the pure solvent is equal to the vapor pressure of the solid solvent. So Tf naught, it is the freezing point of the pure solvent, and Tf, this is the vapor pressure of the solution, because at this temperature vapor pressure of the solution is equal to the vapor pressure of the pure solid solvent. So this is Tf is the freezing point of the solution, because at this temperature vapor pressure of the solution is equal to the vapor pressure of the pure solid solvent. So according to this graph, freezing point of pure solvent is greater than the freezing point of the solution. So delta Tf is the difference between the vapor pressure of delta Tf is the difference between the vapor pressure of delta Tf is the difference between the freezing point of the pure solvent and freezing point of the solution. So this delta Tf is known as depression of freezing point. So when a non-volatile solute is added to a pure solvent to prepare a solution, then vapor pressure is decreased and freezing point of the solution is decreased. So that decrease in freezing point due to the addition of a non-volatile solute in a pure solvent is known as depression of freezing point, which is denoted by delta Tf. So delta Tf, how can you calculate delta Tf? From this point to this point, this is the delta Tf. So how can you calculate delta Tf? Delta Tf is the difference between Tf naught, freezing point of pure solvent, and freezing point of solution. So this is the relation to find out delta Tf. So delta Tf equal to Tf minus Tf naught. So delta Tf, depression of freezing point or lowering in freezing point, equal to freezing point of solution minus freezing point of the pure solvent. It has been experimentally observed that delta Tf, depression of freezing point, is also directly proportional to molar concentration of the solution. To remove the proportionality sign, let us put a proportionality constant Kf. Here a proportionality constant. Here Kf is known as molar depression constant, or it is also known as cryoscopic constant, and its unit is Kelvin kilogram per mole. Now delta Tf equal to Kf, small m is the molality equal to W2 weight of solute into 1000 divided by molar of mass of solute M2 into weight of solvent W1. So this is the final relation on depression of freezing point. So in this relation, W2 weight of solute in the solution, M2 molecular mass of solute in the solution, and W1 weight of solvent. So with the help of this relation, we can find out molar mass of solute in the solution. So fourth one, colligative properties, is osmotic pressure. So osmotic pressure is related to a phenomena which is known as osmosis. So osmosis is a process It is a phenomena in which solvent molecules are flowing from pure solvent into solution, or solution of low concentration into solution of higher concentration through a semi-permeable membranes. So osmosis ऐसा एक प्रोसेस है, ऐसा एक फेनोमेना है जहाँ सॉल्वेंट पार्टिकल्स फ्लो होता है फ्रॉम प्योर सॉल्वेंट इनटू सॉल्यूशन और सॉल्यूशन ऑफ low concentration into solution of higher concentration through a semi-permeable membranes. Semi-permeable membranes are allowing only solvent molecules to flow through it. Solute particles are not allowed to flow through the semi-permeable membranes. So during the osmosis, solvent particles are flowing from solution of low concentration into solution of higher concentration. Why? Because low concentration solution में solvent का quantity ज़्यादा होता है, higher concentration solution में solvent का quantity कमती होता है. Normally higher concentration solution से lower concentration solution बनाया जाता है by the addition of more and more solvent. So osmosis are always taking place from low concentration solution into higher concentration solution through a semi-permeable membranes. So through the semi-permeable membranes from low concentration solution into higher concentration solution कब तक ऑस्मोसिस होता है? जब तक दोनों सॉल्यूशन का बीच में इक्विलिब्रियम एस्टैब्लिश नहीं होता है. दैट मीन्स जब तक दोनों सॉल्यूशन का कंसेंट्रेशन इक्वल नहीं होता है. सो लो कंसेंट्रेशन सॉल्यूशन टू हायर कंसेंट्रेशन सॉल्यूशन, सॉल्वेंट molecules are flowing through the semi-permeable membranes. कब तक फ्लो होगा? जब तक दोनों सॉल्यूशन का कंसेंट्रेशन इक्वल नहीं होगा. सो solution of low concentration is separated from the solution of higher concentration by a semi-permeable membranes. So here one piston is fitted in the higher concentration solution. So osmosis takes place now. That means solvent molecules are flowing from the solution of low concentration into solution of high concentration. So volume of the higher concentration solution will be decreased, then concentration of the volume of the higher concentration solution is increased and concentration of the solution will be decreased. So due to increase in volume in the higher concentration solution, then piston moves upward direction. Suppose हम लोग अभी ये जो डायरेक्शन ऑफ ऑस्मोसिस को हम लोग जस्ट स्टॉप करना है. सो ऑस्मोसिस को हम लोग जस्ट स्टॉप करने के लिए हम लोग क्या करना पड़ेगा? पिस्टन का ऊपर में हम लोग प्रेशर अप्लाई करना पड़ेगा. सो जितना मिनिमम प्रेशर अप्लाई करने से जस्ट ऑस्मोसिस स्टॉप हो जाएगा, that amount of pressure is known as osmotic pressure. So minimum pressure is required to just stop the osmosis is known as osmotic pressure. So the minimum pressure is required to applied on the piston to just stop the osmosis is known as osmotic pressure, and it is denoted by the symbol pi. So जितना minimum pressure apply करने से piston का ऊपर में just osmosis stop होगा, that amount of the pressure is known as what? Osmotic pressure. So osmotic pressure pi of a solution is directly proportional to the molar concentration of the solution at a constant temperature T. What is C here? C is the molar concentration of the solution. Molar concentration. Molar concentration means concentration of the solution in molarity. Here T is the temperature in Kelvin scale. To remove the proportionality sign, let us put a proportionality constant R, which is known as universal gas constant, also known as ideal gas constant. R is the ideal gas constant or universal gas constant. So here molar concentration C, how can you calculate? This is molar concentration C is equal to number of moles of solid dissolves in per liter of solution, volume of the solution V into T. Now pi into V equal to N2 R into T. This is one of the mathematical relation on the osmotic pressure. What is N2 here? N2 is the number of moles of solute. So how can you calculate N2? N2 we can calculate number of moles of a solute in the solution. We can calculate by dividing given mass of the solute by the molecular mass. So now this relation becomes pi into V equal to W2 divided by M2 R into T. So this is the ultimate mathematical form on the osmotic pressure. So what is pi here? Pi is the osmotic pressure, V is the volume of solution, W2 it is the weight of solute in the solution, M2 molecular mass of solute, and R it is ideal gas constant, and T is the temperature in Kelvin scale. So with the help of this relation we can find out molecular mass of the solute in the solution. Two solutions having same osmotic pressure are known as isotonic solution. Suppose osmotic pressure of the first solution is pi 1 and osmotic pressure of the second solution is pi 2. If pi 1 equal to pi 2, then that two solutions are known as isotonic solution. So कब दो सॉल्यूशन का ऑस्मोटिक प्रेशर इक्वल होगा? दो सॉल्यूशन का ऑस्मोटिक प्रेशर इक्वल होने के लिए दोनों सॉल्यूशन का कंसेंट्रेशन इक्वल होना पड़ेगा एट ए कांस्टेंट टेम्परेचर. सो एट ए कांस्टेंट टेम्परेचर जब दो सॉल्यूशन का कंसेंट्रेशन इक्वल होगा, दोनों सॉल्यूशन में सॉल्वेंट सेम होगा, ऑल्दो सॉल्यूट इज डिफरेंट, देन सॉल्यूशन दोनों सॉल्यूशन का ऑस्मोटिक प्रेशर इक्वल होगा. Then that two solutions are known as isotonic solution. Suppose first solution का osmotic pressure pi 1 is greater than the osmotic pressure of the second solution. That means first solution का concentration second solution से ज़्यादा है. Then first solution with respect to second solution is known as hypertonic solution. जब फर्स्ट सॉल्यूशन का ऑस्मोटिक प्रेशर सेकेंड सॉल्यूशन से कमती होता है, देन फर्स्ट सॉल्यूशन विथ रेस्पेक्ट टू सेकेंड सॉल्यूशन इज नोन एज हाइपोटोनिक सॉल्यूशन. सो डायरेक्शन ऑफ ऑस्मोसिस फ्रॉम द लो कंसेंट्रेशन सॉल्यूशन टू हायर कंसेंट्रेशन सॉल्यूशन थ्रू ए सेमी परमेएबल मेम्ब्रेन्स. We can reverse the direction of osmosis. So direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. This phenomena is called reverse osmosis. To reverse osmosis, it is a process in which solvent molecules are flowing from solution of higher concentration to the solution of lower concentration through the semi permeable membranes. So osmosis का डायरेक्शन रिवर्स करने के लिए हम लोग क्या करना पड़ेगा? पिस्टन का ऊपर में प्रेशर अप्लाई करना पड़ेगा ग्रेटर देन द ऑस्मोटिक प्रेशर. So what is the condition for the reverse osmosis? So pressure applied on the piston must be greater than the osmotic pressure. जब पिस्टन का ऊपर में हम लोग ऑस्मोटिक प्रेशर से ज़्यादा प्रेशर अप्लाई कर देगा, देन ऑस्मोसिस का डायरेक्शन रिवर्स हो जाएगा. दैट मीन्स सॉल्वेंट मॉलिक्यूल्स फ्लो करेगा from the solution of higher concentration into solution of lower concentration. Then that phenomena is called reverse osmosis. So reverse osmosis, it is used for the desalination of seawater. Desalination means removal of different salts from seawater. So seawater is containing different salts. So to remove the seawaters, to remove the different salts from seawater, we can use the process of reverse osmosis. So this is the schematic diagram for the removal of different salt from the seawater. This container is containing seawater, this container is containing fresh water. So fresh water is separated from the seawater by a semi-permeable membranes. So this is the piston. When pressure applied on the piston, is greater than the osmotic pressure. Pressure P applied on the piston is greater than the osmotic pressure pi. Then direction of osmosis becomes reverse. That means seawater से प्योर वाटर मॉलिक्यूल फ्लो करेगा टुवर्ड्स द फ्रेश वाटर, और फ्रेश वाटर में क्या होगा, कंटेनर में वॉल्यूम बढ़ेगा, देन हियर ओवरफ्लो होके अनदर कंटेनर में क्या होगा, फ्रेश वाटर डिपॉजिट होगा. सो दिस इज द स्कीमेटिक डायग्राम for the desalination of sea water. So reverse osmosis process is used for the desalination of sea water. Thank you.